Hello everyone, I hope you're all doing well, and today is the class number 39, and we only have one more class, like kind of lecture class. We have 40, and now 41 is going to be for the exam. So today we are going to talk about some chapter 11 from the Wiley Plus. Here the section numbers or chapter numbers are a little different, but you can follow the topics and check the prior reading assignments before looking at this, okay? So today we are going to talk about combined motion, and we were kind of setting the stage for this. We learned about translational motion, we learned about rotational motion. Now this is the time to put these together so that we can look into more complex problems. And so we will start with rolling motion. And first we will ask some questions, okay? So for example, when your car is stopped and you floor it, what happens then? At that moment, tire slips, right? And if you're on a gravel road, it will throw rocks around the car. And when you're driving down the road, does the same thing happen? The answer is no. In general, again, if it's not really a gravel road and kind of simplified case. And so in normal driving, the tire does not slip, right? And relative to the road, that's why it doesn't really throw stones as it should. And does the car wheel rotate, and about what point? Okay, so we are going to investigate some of those things. Those are kind of warm-up questions just to kind of have you focus on the case. So first of all, we'll consider the motion of the wheel if it was jacked off the ground with the accelerator depressed and the wheel undergoes pure rotation. So here we have rotation case, okay? And first of all, the tire is, or the wheel is rotating clockwise, as you can see, omega direction. And we are going to focus on 3 points: the top, the center, and the bottom, okay? And we are going to think about since this is rotation, what are the velocities related to rotational motion? So what is the tangential velocity related to the angular velocity? So as you already know, the relation between the tangential velocity and the angular velocity is simply v is equal to omega r, right? And r is from the rotation axis to the point of measurement that you're doing for the tangential velocity. So here, if you look at the top, since this is pure rotation, it is rotating around the center, so that's your pivot point, right? Again, remember that it is important to see where the pivot points are, just like kind of determining your origin, right? So we need to know where the rotation axis is. This is pure rotation, okay? So that's the center is the pivot. So when you are calculating the velocity, you need to get that omega. Omega is the same for any point on this wheel, and so the only thing that changes depending on your location on the wheel, r changes. So at the top and the bottom, r is the same because of the pivot is right at the center of those 2 points, right? And they're both capital R. So you can write the velocity magnitude in terms of omega r, and the same thing for the bottom point. So the directions come from the kind of the omega direction, so it's going clockwise, right? And the tangent at the top, thinking about clockwise rotation, should be to the right. And again, think about the clockwise rotation at the bottom. The tangent line should be to the left. That's the direction of the velocity, okay? And they are the same. That's the important part. And then we will think about now pure translation. Okay, so let's focus on that. So in reality, the wheel also translates with the car. So this is what the translational case is. And VCM is the velocity of the center of mass of the car, right? And since the wheel is moving with the car, translationally, it is going to have the same center of mass velocity. Once again, we are focusing on those 3 points, okay, top, center, and bottom. And this is translation. There's no rotation. There's no pivot point or anything like that. We're just looking at pure translation. So whatever the car's speed is or velocity is, then you will every point on the wheel will pick up the same speed, right? So that's why, as you can see, they have the same magnitude, same velocity. Again, these are also linear velocities. So we discussed the rotation and the translation, the motion. Now we are going to put them together. What we want is the combined motion. So this is our rotational here, and this is our translational. We need to add them up, and we are going to discuss how we get this. To be able to get that, first we need to see something. Let's focus on the bottom point, okay, right here. So when you have a combined motion, where is the pivot point? Is it still at the center of the wheel? Remember, it's also moving in a translational motion. So if you observe a kind of a wheel, or choose like some sort of cylinder or some round object and try to roll it, where does it rotate from? It rotates from that bottom point where it touches the surface, okay? So that is going to be the pivot point now. Okay, so if you go here, this is the pivot point for the combined motion. Okay, this is important. So at that point, the pivot point is not moving, right? Because it's a pivot point, it's fixed point. That means you have two velocity vectors, omega r and v center of mass. These two should be the same. So this is the explanation of that. We are saying that to the right is positive, so to the left is negative. So negative omega r plus v center of mass equals to 0. It should be, right? And you get the center of mass velocity to be omega r. Now thinking about the top, so look at these two. If this is also omega r, then you have two of those. That's why you get two of the center of mass velocities. At the center, this is 0 and this is center of mass velocity, so you have only one of them. Okay, so for the combined motion, this is what you get. Hopefully that makes sense now. So that means if you look at this equation here, v center of mass is equal to omega r. If you know your car speeds, right, v center of mass, and your tire radius, you can also determine the angular velocity for your tires. So effectively, the tire pivots about the contact point with the ground, as we showed on the figure, and this contact point continuously changes as tire moves. So it's instantaneous pivot point. Okay. Next, we will talk briefly about the kinetic energy for combined motion, and then we'll start solving some examples. For this case, so as we noted before, the kinetic energy for an object that translates and rotates would be the sum of the kinetic energies associated with each motion, right? So if we have a translational, then we have kinetic KT basically in the equation. And if we have rotation, then we also have KR. Since this is combined motion, we have both of them. So simply total kinetic energy is going to be a combination of those. And you can see that. And you're just writing, this is the translational kinetic, but you need to think about, it's like now you don't have a point particle, right? It is a rigid body. So you have to think about a center of mass. And the same thing for the rotational kinetic. This inertia, moment of inertia is for the center of mass of the object. So, and we already kind of started using this anyway, but now we are going to apply it to the other problems as well in the next video.